Welcome to G Fun Facts Online. Today we're talking about something invisible, yet vital, that's on the move. Deep beneath our feet, a battle is raging, and it's pulling one of our planet's most fundamental features off course. The magnetic North Pole, the point your compass needle desperately tries to find, is not where it used to be. For centuries, it was content to wander slowly around the Canadian Arctic. But now, it's in a race, a mad dash across the globe towards Siberia, moving at a staggering speed of up to 55 kilometers, or 34 miles, every single year. This isn't just a quirky geographical fact. It's a sign of immense and turbulent forces churning at the heart of our world, with real consequences for our technology, for animal migrations, and for the very shield that protects us from space. So what's causing this dramatic shift, and what happens when north isn't north anymore? For centuries, magnetic north was a ghost, a theoretical point that sailors relied on but couldn't pin down. It wasn't until 1831 that someone actually stood there. British explorer James Clark Ross, on a grueling expedition in the Canadian Arctic, used an instrument called a dip circle. He was looking for the one spot on Earth where the magnetic field lines point straight down. On June 1st, on the Boothia Peninsula, his instrument read 89 degrees and 59 minutes. He was there. He built a small monument of stones, marking the location of the magnetic North Pole. But even then, Ross noted that the pole wasn't perfectly still. It was a hint of what was to come. Over 70 years later, in 1904, the legendary Norwegian explorer Roald Amundsen, during his historic first trip through the Northwest Passage, made it a mission to find the pole again. And he did. His measurements confirmed it. The pole had moved. It wasn't a fixed spot on a map, but a wanderer. Throughout the 20th century, scientists, mostly from Canada, continued to track its position. For decades, it drifted slowly, predictably, at a pace of about 15 kilometers or 9 miles per year. But then, in the 1990s, everything changed. The pole hit the accelerator. Its speed more than tripled to that astonishing 55 kilometers per year. It was rapidly leaving Canadian territory behind, heading for open ocean and pointing directly at Siberia. This sudden sprint signaled a dramatic change deep within the planet, launching a new era of intense scientific investigation. To understand why the pole is moving, we have to travel to the center of the Earth. Forget the idea of a giant bar magnet in the core. The Earth's core is hotter than the sun's surface, a temperature at which any permanent magnet would instantly lose its power. Instead, our magnetic field is generated by what's called a geodynamo. Our planet has a solid inner core made of iron and nickel, surrounded by a liquid outer core of the same molten metals. Heat from radioactive decay in the inner core creates massive, swirling convection currents in this ocean of liquid metal. As this electrically conductive iron flows and churns, influenced by the Earth's spin, it generates powerful electric currents. These currents create a self-sustaining magnetic field that wraps around our entire planet. But this engine is not smooth and steady. It's turbulent and chaotic, and it's this turbulence that causes the magnetic poles to wander. Thanks to data from the European Space Agency's Swarm satellite mission, we now have a much clearer picture of what's happening. The current rapid shift is the result of a titanic tug-of-war between two massive blobs of molten iron with negative magnetic flux, located at the boundary between the core and the mantle. For centuries, a huge magnetic blob under Canada was the dominant force, keeping the North Pole tethered to its region. But in recent decades, this Canadian blob has been weakening and elongating. At the same time, a rival blob under Siberia has been growing stronger. This power shift is a direct result of changes in the flow of molten iron that happened between 1970 and 1999. The Siberian blob is now winning the tug-of-war, pulling the magnetic North Pole relentlessly towards it. This discovery is a crucial window into the complex, dynamic processes that govern our planet, and it has very real consequences for us up here on the surface. The most immediate impact of the wandering pole is on navigation. Everything from a simple hiking compass to the advanced systems in aircraft and ships relies on knowing the difference between true geographic north and magnetic north. This angle is called magnetic declination. As the pole moves, this angle changes everywhere on Earth, making existing magnetic charts obsolete. This is why we have the World Magnetic Model, or WMM. It's a comprehensive map of the Earth's magnetic field, maintained by agencies in the US and the UK. It is the standard model used in countless navigation systems. The military, including NATO, the US Department of Defense, and the UK Ministry of Defense, uses it for everything from aircraft and submarine navigation to parachute deployment. Commercial airlines and cargo ships depend on it for accurate headings, especially where GPS might be unreliable. Even airport runways are named based on their magnetic heading. As the field shifts, runways have to be renamed. In 2011, for instance, Tampa International Airport had to repaint a runway to account for a shift. And that smartphone in your pocket? Its map and GPS apps use the WMM to orient the map correctly and give you accurate directions. The WMM is normally updated every 5 years. The changes are usually slow and predictable. But the pole's recent erratic sprint forced an unprecedented emergency update in 2019. The existing model had become so inaccurate, it was nearing the limits of acceptable error for navigation. It was a stark reminder of how unpredictable the Earth's core can be. And just to be clear, GPS itself doesn't use the magnetic field to find your location. It uses signals from satellites. But the digital compass, or magnetometer, inside your GPS device does rely on the World Magnetic Model to know which way you're facing. Humans aren't the only navigators on this planet. A vast array of animals has evolved an incredible sixth sense, known as magnetoreception, allowing them to use the Earth's magnetic field to guide their epic migrations. Many birds, from the tiny European robin to the Arctic tern, which travels from pole to pole, use the magnetic field as a compass. Some scientists believe they have tiny magnetic particles in their beaks that act like a compass needle. Others point to a protein in their eyes that may allow them to literally see the magnetic field lines. Sea turtles, like the loggerhead, embark on transoceanic journeys, returning to the exact beaches where they hatched. They are thought to use the magnetic field not just as a compass, but as a map, sensing variations in its intensity to get a rough idea of their location. Whales, salmon, and even some insects are also believed to use this sense. A rapidly shifting pole and a weakening field could potentially confuse these natural navigators. While many animals are adaptable and use other cues like the sun and stars, a significant and fast change in their primary compass could still pose a challenge. The good news is that looking back through the fossil record, past major magnetic shifts don't seem to be linked to mass extinctions, suggesting that life has found ways to adapt over geological time. Beyond navigation, the magnetic field serves a far more critical role. It's our planet's shield. This invisible force field, called the magnetosphere, protects us from a constant barrage of charged particles from the sun, known as the solar wind, and high-energy cosmic rays from deep space. And this shield is weakening. The field's strength is currently decreasing at a rate of about 9% per century. A weaker shield means more harmful radiation can penetrate our upper atmosphere and reach closer to the surface. This poses a significant threat to our modern technology. Satellites in low Earth orbit are especially vulnerable. Increased radiation can fry their sensitive electronics, causing malfunctions and shortening their lifespan. There's already a well-known weak spot in the magnetic field called the South Atlantic Anomaly, stretching over South America and the southern Atlantic Ocean. Satellites passing through this region regularly experience glitches. A global weakening of the field could make problems like this more common everywhere. On the ground, our power grids are at risk. Intense solar storms can induce powerful electrical currents in long conductors like power lines. These currents can overload transformers, potentially causing widespread, long-lasting blackouts. A weaker magnetic field makes our grids more susceptible to these solar punches. It can also disrupt radio communications and any systems that rely on a stable ionosphere. The accelerated wandering of the pole and the weakening of the field inevitably lead to a huge and unsettling question. Are we on the verge of a complete magnetic reversal? A geomagnetic reversal is exactly what it sounds like. The north and south magnetic poles swap places. What was north becomes south, and what was south becomes north. We know this happens because the Earth's magnetic history is frozen into its rocks. When volcanic lava cools, tiny iron-bearing minerals inside it align with the magnetic field at that moment, creating a permanent record. This field of study, called paleomagnetism, has shown us that reversals are a regular, if unpredictable, feature of our planet's past. The geological record shows hundreds of reversals over the last 160 million years. On average, they happen every 200,000 to 300,000 years. The last full reversal, known as the Brunhes-Matuyama reversal, was about 780,000 years ago. This has led some to suggest that we are, statistically speaking, overdue for another one. But a full reversal isn't like flipping a switch. The process is thought to take thousands of years. During this transition, the main magnetic field weakens significantly and becomes much more complex. Multiple, temporary north and south poles could pop up all over the globe before the field settles into its new, reversed orientation. There are also shorter-lived events called geomagnetic excursions, where the poles wander dramatically and the field weakens, but they don't fully flip. The most recent and well-studied of these was the La Champ event, about 42,000 years ago. During this excursion, the magnetic field strength dropped to as low as 5% of its current power, and the poles briefly swapped places before snapping back. Some studies have linked the La Champ event to major climate shifts, and even the extinction of Neanderthals, though this is still heavily debated. So, can we predict the next one? The honest answer is no. The chaotic, turbulent flow of liquid metal in the outer core makes long-term forecasting incredibly difficult. While models can predict the field's behavior a few years out, forecasting a reversal centuries or millennia in advance is currently impossible. The rapid pole drift and the weakening field are intriguing clues, but they are not a definitive sign that a reversal is imminent. The field has fluctuated like this in the past without flipping. Scientists are working constantly to improve our understanding, using more sophisticated computer models and data from satellites and ground observatories. The shifting north is a powerful reminder that we live on a planet that is alive and constantly changing, from its surface right down to its fiery core. While a full magnetic reversal might sound like science fiction, the present-day movement of the pole is a reality with tangible effects. Our increasing reliance on technology that is vulnerable to these magnetic changes makes it critical that we continue to watch, to measure, and to understand. The work being done to update the world magnetic model and to improve our forecasting is essential for the safety and reliability of the global systems we all depend on. The story of the shifting north is far from over. The pole will continue its journey, pulled by the unseen turmoil thousands of kilometers below our feet. As it wanders, it will continue to challenge our science and our ability to adapt, reminding us of the power and mystery of the natural world, a world that is always in motion.